Okay, we are ready. Almost ready. Now we're ready. Questions on chapter 3 homework? What did it say?
Use the method 3.2 to approximate the square root of 26, using square root of 25 as an estimate.
So I'm going to approximate square root of 26 using square root of 25 and
25.5.
And 25.5. And I want this in context of 3.2?
Yes.
Right, so 3.2 is that equation that says f of x plus delta x is approximately equal to
f of x plus f prime of x plus delta x divided by 2 times delta x.
Okay, so that's ultimately what we're going to do. This was like one of the examples I did last class. So basically we are going to start out with our function f of x is radical x, which f prime of x would be 1 over 2 radical x. And so I'm going to use the fact that I know what radical 25 is, so I know what f of 25 is. That's just radical 25 equals 5. And I also know what f prime of 25 is, which is 1 over 2 radical 25, which is 1 over 10. Here I'm going to let my x be 25, my delta x be 1. Right? And then I'm going to try to do this. So we want f of 26, which is just f of 26 plus 1, 25 plus 1. Right? So this is my x and my delta x. So I'm going to approximate that using this formula. That's f of 25 plus f prime of 25 plus this over 2, right? So that's plus 1 over 2 times delta x, which is 1. So this is f of 25 plus f prime of 25.5. So this I know is 5, plus this is 1 over 2 radical 25.5. And so this is why it said you need to use this guy. At some point you're going to end up with a number here that you're not going to know what the exact answer is, so you're going to want to approximate that. So you go to one side, and now we're going to approximate this one with theorem 3.1. Approximate with 3.1. So I'm thinking of this as a whole new situation now. I want to get 25.5. So similarly, my f of x is radical x. My f prime of x is 1 over 2 radical x. Here I'm taking x to be 25 and my delta x, which is a completely new one, to be 0.5. And then I'm going to find f of 25.5 is approximately equal to f of 25 plus f prime of 25 times delta x. Right, this is 3.1. So that's going to be 5 plus 1 over 10 times 0.5. And this was what?
5.05.
5.05. And then I'm going to plug that back in here. So this is equal to 5 plus 1 over 2 times 5.05. Which is what? 5.09906. And that's
0, 0.
Huh?
0, 0.
And that's how it's done. Right, so you start out with theorem 3.2, but in theorem 3.2 you'll always get to a position where you need to use theorem 3.1 to figure it out, and then come back. So when we're doing this in the table, that's the part where we had to do that theorem 3.1, but we used delta x over 2 in order to compute it. Yes? Questions? Okay. Other questions?
Did you do 7?
What does that say? Does anyone have the book?
You want to know the question? The question?
Yeah, I need to know what question 7 is. So problem 7 says the value of ln2 can be obtained from the solution to. We can find ln2 from the solution to y prime equals 1 over x and y of 1 equals 0, and it says how. This is part A. How would you obtain the value of ln2?
You have to
Separate the variables. So here I have dy dx is equal to 1 over x. This means that dy is equal to 1 over x dx. I can integrate both sides. So here I have y is equal to ln x plus c. And so now I apply the initial condition. Y of 1 equals 0 implies that when I plug in x equals 1, I get y equals 0. What's ln of 1? Log of 1 is 0, which means that c equals 0, which means that y equals ln of x is the solution to this differential equation. And so at this point, plugging in 2 into the solution of the ODE gives us ln2. Of course, we can also approximate ln2, which I think is what leads into part B. Right, so ultimately you can think of ln2 as being the solution of this evaluated at a certain point. That's what part A is trying to get you to understand. Part B actually asks you to do it. So in part B it says, based on your answer to A, use Euler's method with 4 subintervals to estimate the value of ln2. So because I know ln2 is obtained from the solution to this, all I want to do is approximate the solution to this, right? Using how many subintervals they told us. For part B, note we can estimate the value of ln2 by approximating y of 2 in part A. So now this becomes a question of, given this differential equation with that initial condition, approximate y of 2. And how would we do that? What's the first thing we need to figure out?
X.
X? No.
Delta X.
Delta x. What would delta x be? 2 minus 1
2 minus 1.
over 4. How do you know that?
Because y1 is your A, and y of 2 is your B. So it's B minus A, which is 2 minus 1.
B minus A are x values, remember that.
Yeah, right, so
Right, so this
values
guy
inside.
here is the x value you want to approximate, that's your B,
Yeah.
right? So it's an x value.
Yeah.
And this guy here, the one that you started with, is your A. So you take the last x value minus the initial x value, that's your B minus A, divided by n. N is the number of subintervals you're using, and they told you here in the question they want you to use 4. So then we know our delta x is this guy, which is 0.25. And so now we can start doing that table. Here's my x, here's my y, here's my y prime equals 1 divided by the x value. I'm going to start the x value at 1, my initial y is 0, and my x is going to keep on increasing by 0.25 until I get to 2. So it goes to 1.25, 1.5, and then 2. 1.75 and 2. So, see if you guys are paying attention. Right? And the answer here is what we want, which means I don't care about what's here. So we're just going to do Euler's method running this through. So what is this going to be?
1 over x. So it's
1 over the x value, which is just 1. So this is 1. And at this point, everywhere here, we're using theorem 3.1. So I'm always going to be taking y old plus y prime old times delta x. So here, old y is 0 plus old y prime, 1 times delta x is 0.25. So this gives me 0.25. What's my y prime?
1 divided by 1.25.
1 divided by the x value, which is 1.25.
0.8.
0.8 exactly?
Yes.
Okay, so then now we move on to the next step. Again, I'm going to use y old, y prime old. So here the old y is 0.25 plus the old y prime, 0.8 times my delta x, which is 0.25.
0.45.
45. What's my y prime? 1 over 1.5, because the formula is 1 over x, so I take 1 over the x value.
0.57.
Exactly?
No. It's 142.85714.
Go to this one. What goes here? 0.45, which is the old y value, plus 0.5714 times 0.25. What does that give me?
0.5929.
5929.
That's wrong. No? 1 over 1.5 is equal to
1 over 1.5?
Yeah, 0.666. 6 would be it.
0.6667.
Yeah, use 1 cent, but yeah.
So this would be here. 6667. And this becomes what? 0.6167. So it would be 6168. What's this one? 1 divided by 1.75, which is what? 0.5714. Okay, which was the last one. Okay, so now I take the old y, 0.6168, plus the old y prime, 0.5714, times my delta x, which is 0.25, and ultimately I get what? 0.7596?
Yeah.
That's pretty close to LN2. I think LN2 is like 0.69 something.
0.6931.
Yeah, so.
How many decimal places do you recommend we stick to?
One more than how many I asked for. So in general, on a test, I'll tell you how many I want. I say approximate this to 3 decimal places, in which case, work in 4 decimal places and then round to the third for the final answer. Yeah, so I'll tell you how many decimal places I want you to use. Maybe one more question?
13. 8 is just horizontal.
And then referring to exercise 6, use modified order block. Okay, so this brings me back to exercise 6, which said what? Okay, so problem 13 referred us back to problem 6, which asks us to approximate E. It's very similar to problem 7, but now they ask us to approximate E instead of approximate LN2. Problem 6, I actually did that in class. That was actually an example. Yeah, so problem 13, prepare a table similar to 3.2. Yeah, so here, they didn't tell us how many subintervals they wanted us to use.
No. Well,
13?
Yeah, for problem 13.
they did. They did
Instead of
4. The
Four
tax would have been
subintervals
0.25.
From 0 to 1.
Oh, you mean in problem 6 they told us use 4.
In problem
No,
13A, it says 4 subintervals.
Use
The-
Euler method. Oh, 4 subintervals. That's crazy. That's gonna take forever.
Or at least give us the first two.
Like in a test, I'd ask you to use 2.
Oh.
I'm not gonna ask you to use Euler modified Eulers with 4.
That's sweet. In the homework, you asked us to do 4.
Because if you can get through 2 rows, I know you know how to do it, right? 4 is just overkill.
Does that apply to the test?
Yes.
Does that apply to this one?
Well, the homework you have to do it what they say, but just know if you can get through 2 rows, you're good. We're good. That's all we need to know. So yeah, I'll just jump into the table thing.
Yeah.
So X. So this is problem 13. X, Y, Y prime. Well, Y prime here is equal to Y. X half, Y half, Y prime half is equal to, it'll be the Y value here, Y half.
How do you know that y prime is equal to y? Where in the
In problem 6 it told you that.
Oh, that's
So in problem 13 it says refer to exercise 6, in which case they gave us this in exercise 6
okay.
with an initial condition.
I think that was everyone's question.
So it's y of 0 equals 1.
Okay.
So this is from problem 6. And so I know I'm starting with 0 and 1. In this case, my delta x is again 0.25 because I'm using 4 sub. Is it 0.25? Because I'm going from 0 to 1.
Yes, it's 1 over 4.
Yeah. So it's going to be 0.25 again. So this is 0.25, 0.5, 0.75, 1. Now start, and I can automatically fill out these guys. So half of 0.25 is what? 0.125. So 0 plus 0.125. And then I keep adding 0.25, right? So this would give us what?
Oh, 0.375, 0.625, 0.875.
Okay, and I don't care about anything else. Right? This I won't care, this I don't care, this I don't care. Okay, so the x's are filled out. Now let's start getting the y's on. So 0, 1, my y prime is going to be what? 1, because it's just whatever the y value is. I'm just copying it down.
That means that that's 1.1.
Y half. How do I find y half?
Y old
Y old
plus
plus
y prime
old
old
times
delta x divided by 2.
delta x over 2. Okay, that's always going to be the formula I'm using here. So I take the old y, 1 plus y prime, which is also 1, times delta x over 2, which is 0.125. So I get 1.125 here. My y prime uses these two values in the formula. So it just, again, copies the y value. So this column is going to copy that column. This column is going to copy that column because that's the formula we're given. So this is just 1.125. Then you go over here, and over here we're using theorem 3.2. So the formula we're always going to use here is y old plus y prime half old times delta x. Right? So I'm always using the old y, this y prime with delta x. So this is 1 plus 1.125 times delta x, which is 0.25.
What if y 1/2 be 2.121?
How?
Oh, no, never mind. Never mind.
Yeah.
It was a dumb thing.
So this is
1.281, I think. Yeah.
Yeah.
right, and then this will just copy that 1.281. This will be the old y, 1.281, plus the old y prime, again 1.281, times delta x over 2, 0.125.
1.441.
1.441, which this derivative will be 1.441. Do it again. The old y, 1.281, plus this y prime, 1.441, times delta x, 0.25. And that gives me?
1.4611.
And this just copies that, 1.4611. Because this just tells me it copies whatever the y value is. Go over here, old y value, 1.4611 plus old y prime value, 1.4611 times delta x over 2, which is 0.125. That gives me
1.6437.
6437. This copies it, 1.6437.
I think that number is wrong.
Please check it.
1.461. I think it's 1.641. Yeah.
1.64?
Yeah.
Which means this 1.64. 1.64. Does that look okay?
So now this is gonna be 1.8469 for y half. Yeah.
1.8469.
Yeah.
Make sure you guys are doing this in your calculator all at the same time, so you engage that muscle memory. The more of your senses you put into learning something, the better you learn it. Okay, so now again, old y, 1.4664, 1.6411 plus the y prime from way over there, 1.8469 times delta x, which is 0.25, and that gives me
2.695.
2.6.
Oh my god, 2.1034.
2.1034. Which this would give me 2.1034. Over here, old y, 2.1034 plus old y prime, 2.1034 times delta x over 2, which is 0.125.
2.3663.
2.3663. This copies that, 2.3663. Finally, old y, 2.1034 plus old y prime over there, 2.3663 times delta x, 0.25, and we will finally have our approximation.
2.6949. Or
This means y of 1 is approximately equal to 2.69.
or no, or you can just 2.6950 to round up.
750. Right, which is okay rounded to 1 decimal place, because remember it's 2.710.
2.71.
So you see, it sort of gets repetitive. You just know I take the answer over here plus the answer over there times this.
Muscle memory.
Yeah, it's essentially muscle. Yeah, we'll stop there. So yeah, like I said on the test, I'd only ask you to modify like 2 rows. You'd only have to do this like up to here. If I'm asking you Euler's method, I'd ask you for at least 4 rows because that one's a lot simpler. But they're both a matter of, it's almost muscle memory. You do enough, you sort of just know what to plug in. You want to shift. So, yeah, that's it. We're going to move on. This I don't think we'll get to today, but I will get to it very soon, so you might. So just hang on to these, keep them with you, and we're going to use them when we get to chapter 5. For the most part, chapter 4 should take 1 lecture. I don't know if it'll take a whole.
Hey, are we taking the entire period for the test next week?
What?
The entire period? Is it going to take the entire period? The test?
No, the test will be maybe an hour and 15 minutes.
And do we have lecture?
I'll probably lecture after you. So why not? I mean, we're all here.
I have one question.
Yes.
It's not about the homework.
What is it?
So it is about the homework, but it's not a question. So you know for this homework we had 1 to 11 on 13, 8, and then we had 17 through 19 which required the Excel, I believe.
Okay.
Would this count as 2 homeworks? Would this be like the Excel homework plus a regular homework?
No, just can't put it all in.
So you know how you said you don't drop the lowest Excel grade homework wise?
Mhm.
So let's say, would you drop this?
No, I don't know. Excel, the homework rules applies to the Excel, so I will be dropping 2 of your Excel homework as well. So when I'm grading it, I'll have 2 columns. I'll do the written homework, they got it, the Excel homework, they got it.
So today's homework is just the written homework. I'm like kind of confused about it. You guys,
An Excel.
you know what?
Wasn't there Excel for chapter 3?
Yeah.
Yeah, so there's both.
But it wasn't like a separate homework. It was just included in homework 5.
Yeah, do it all at once. Print out your answer and just staple it out in one packet.
Perfect.
Just staple the Excel at the end.
Okay.
Also, for Monday, would it be cool if we have lecture first and then test?
No.
No.
You just don't like that?
I don't think.
Because then,
Oh.
That won't work.
I'm good.
Yeah.
Yeah, so yeah, I agree with
And
that.
we'll have more
Lecture
time.
first, and then-
I got something better. Test, no lecture, no homework.
We'll see.
I got something better than that. No test.
No.
No test.
We have to do a test.
You can't tell.
I may or may not lecture. I'd rather lecture than not, because I feel like we're moving slower.
Okay, but don't even come to me.
Yes. If there's no lecture, no test.
So Mike, before this class, I like 6:55. I talked to myself at 6:40. I walked out. Like I don't even make eye contact with them.
Yeah. That's probably a sign I'm getting older. Like time flies so fast. I feel like I move at the same pace, but like I'm actually behind from where I usually am. So I guess I'm moving extra slow.
Time flies in the
I don't even realize.
How old are you?
Why an hour and 15 minutes?
Because it has 5 questions on it.
What questions are covering what topic or not? You don't know that anymore.
What?
Like, is there a part A, B, C to any of the questions?
It'll look like the review problems. Okay, so that I should probably mention. I sent you guys an email a few minutes ago, maybe half an hour, 20 minutes ago.
Yeah, you did.
I thought you were gonna
It had study advice in it. Right? Because people are asking, how do you study? There's that parts, what's going on? What's going to happen? Right? So watch those videos. I gave a lot of advice. It was for my Calc 3 class last semester. Like, a few people bombed the first exam and I was like, oh my god, here's how you study. Because what happens is I have like this policy. If you get less than a 70 on one of my tests, you have to like meet with me. It's mandatory. And I'm going to figure out what happened and then school. Yeah. You're gonna have to talk. And every semester, what happens is some of the excuses I hear, they don't make any sense. So then I had to give them a talk. And so I recorded the talk, so you guys should watch that where I actually tell you what you should do. I have to give you guys a talk.
Wait,
I need, so
I didn't get your
there are times like, so like I'd ask them, so, why did you do so bad on the test? What happened when you were studying? How did you study? And they'd tell me, So they tell me, so how did you study for the test? Well, I did all the homework and I went over all the quizzes and then I did that. Okay, all right, cool. Did you do all the review problems? No, I did 1 or 2. I did some of them. I didn't do all. Ah, I see. Right? So you hear things like that and then you're like, no wonder you're doing that, right? You're doing completely the wrong thing.
Wait, that's what so my brother's in your class, apparently this liar got his A+. So he said that he was like your 5th top student. He had a 56 average. And then on the final, he like did really well. So you were like, I pity your whole grade.
No.
Is that not what happened? He lied.
The grades in 209 are usually much better than that. You wouldn't have the 5th student being like
Maybe he didn't take 209.
so.
When you say review problems, like
The ones on my website.
on your website, okay.
Yes. Right. So, okay, quiet down. Sir. Be quiet. Be quiet. Okay. So, I'm not going to talk at length because, like I said, I gave this advice before in like an email, on the video. So go watch the video where you'll get extra. But in general, what you want to do is, let me put it this way, especially for part-time instructors like myself, we're overworked and underpaid, right? So if I take the time to do something, right? Like if I sit down and actually go through all the finals and pick out, say, okay, do this problem, and actually take the time to do that, right? It means it's important, right? I'm not going to just do this and like not care about the review problems I did, because that's a waste of my time. And my time is precious to me, right? If I take the time to do something, you should realize, hey, it's probably important, okay? So in general, if a professor like takes the time, gives you a set of review problems, what's the first thing you should do?
Review.
The review problems. Okay, so when I ask the student, how did you study? I did all the homework, I did all the quizzes, I did all this, I did all that. Did you do the review problems? No. They did the one thing they were actually supposed to do, they didn't do. And then they're wondering, oh, I don't know why I'm doing so bad. I don't understand. I studied for hours and hours and hours.
That's what I sound
Right?
like all the time.
Right, so when students get into that situation, it sucks to be in that situation, because you put in the time, you put in the effort, but you're not getting the results, that sucks, right?
That's my life.
So I pretty much tell you on the video how to not be that way.
I didn't even
If you don't study, then I can't help you, right? If you are the person who's going to put in the time and put in the effort, you want to put it in the right way, right? How you do something is just as important as what you're doing, right? Because you can like negate your results if you're doing something wrong, right? You're just doing an experiment and you're using dirty machines, right? Dirty apparatus. It's going to mess up your results. So you're like, I did the experiment. Yeah, but you did it the wrong way, right? It's not going to end up giving you what you want, right? So it's not just what you do, it's how you do it. And then I talk about how you should do certain things, how you should study for my class. Another thing I want to mention is, literally everything I do, I know it doesn't seem like, it doesn't seem this way, but it's actually the truth. Right? Because I always joke around with you guys, and you think I don't seriously take anything seriously. The truth is, I take things super seriously, right? Literally every single thing I do in relation to this class and teaching it, there's a well thought out, conscious reason why I do it, right? Even when I mess with you guys, oh, we have a quiz today, and I'm actually joking with you, there's actually a reason why I do that. There's a reason why I tell you to do everything I ask you to do, right? I explained some of it on that video, but I just want you guys to understand that, right? So don't pay attention is basically what I'm trying to say. Pay attention to what I'm doing, right? Do this for all your professors, in fact. Pay attention to what the professor is doing, right? I have this whole section in the video about knowing yourself and knowing your enemy and all that stuff, right? Where you have to know the enemy, you have to know yourself, and this is how you approach a certain situation depending on who is on the opposite end of the table, all that stuff, right? So I talk about that at length. Watch the video, right? But you should know all that stuff, right? So there's a reason for everything. Everything that's written in the syllabus that I took the time to type out, there's a reason for everything, right? And that's what I want you to know. Also, watch the video to hear more about this. Stephanie made a complaint to me. She made a couple complaints to me today.
Like,
That's Stephanie right there. That's Stephanie right there. She was in the tutoring center today, and she was like, she said two things. She said, one, I'm intimidating. That I don't know why. I think I know why though, because what I did was, yeah, there's a reason why I'm going to talk. Reason for everything. Okay. Sometimes when I tutor you, you come and ask me to help you with something. I'll ask you a question, right? I won't just say, oh, this is the answer. I'll actually ask you a question. A lot of people get intimidated by me asking them questions, because then I ask the question and I stare at them for the answer. Right? So they're like, I don't know what to do, I don't know what to do. They freak out. Right? So here's the thing though. Pay attention to everything I'm doing. There's a reason why I ask you the question. And in fact, there's a reason why I want you to feel uncomfortable when I ask you the question. So I am going to stare at you on purpose. Like, right? There's a reason, right? What do you think the reason is?
Big evil.
The same way.
You feel the same way in a test. When you're on a test and you see a question that you don't understand, oh my God, you freak out, you freeze, you don't know how to deal with it, right? I want you to understand how to dig yourself out that hole, right? So I'm going to ask you a question, I'm going to make you feel uncomfortable, so you understand how to figure something out while you're uncomfortable. You get what I'm saying?
Yeah.
Because it makes a difference, right? If you can do something when everything's calm and everything's hunky-dory and you feel happy and fine, it's a completely different thing doing that in a context where everything is crazy and chaotic around. I want you to get used to the feeling of chaos, the feeling of being nervous, the feeling of, that's why I joke with you about, oh, we have a quiz today. You guys start freaking out, oh my God.
That's my favorite.
I want you to get used to the idea of freaking out. Get used to what it feels like and know how to calm yourself down. Okay? Get used to all that stuff. There's a reason why I'm literally doing everything.
Is this like that
Right?
war story?
Also, it's the war story is a part of it, yeah.
You mentioned it.
Another thing what I'm trying to say is pay attention to literally everything. If I ask you a question when you ask me how to do a certain problem, that same question I asked you is the question I expect you to ask yourself when you're facing that same problem. Right? So there are sometimes when I face a problem, how I figure it out is I actually ask myself questions. Right? So I'll see a problem and the question what is always a good problem. What does this mean? What does that mean? You know? So in a question it might say something and I'd ask the student, so what is this? And I look at them. I don't know. Right? So I think there was some homework on student. No, that's fine. Yeah, so, oh, in fact, on the last quiz, this applies to what was on the last quiz as well. I think on the last quiz I had dy dx equals to x cubed plus 3 plus e to the y. Remember that? And we had, the initial condition was what?
Yes, that question.
It was something like that.
Yeah.
And then I said, we know y of 4 point, or I should write.
Here, you
I
want
think
it?
I actually have it.
I have it here.
Oh, you have the answer. It says y of 0 equals 0. I told you that y of 0.1 was 0.4, and then I said approximate y of 0.2. I could have phrased that another way, right? So I want to actually phrase that another way where it's more complicated. So I can show you how you would dig yourself out of it.
We don't even know how to dig ourselves out of that one.
I don't know how to dig a period.
No, you need to know how to dig. It's very important.
Come on.
My wife is digging my grave for me.
Yeah, because it doesn't illustrate it very well with this. I could also do the homework problem and then illustrate that again. There was also another problem. So I'm going to do this and then I'm going to do this problem. Where it said dy dt is equal to y cubed minus 0.75, 1 plus t, y of 0 equals 1. Part A was find y prime of 0. Part B was use y of 0 and y prime of 0 to estimate y of 0.5 and etc. Right? So this is the problem you're facing with. Let's say I'm faced with this problem. Because I didn't actually, in class, I didn't really show you how to do a problem exactly like this, but I threw it on the quiz because I knew you knew this equation. Right? So if someone came to me and they're like, Jhevon, how do I do this problem? I'd probably ask them something like, what is it that you actually want to do?
That's so ambiguous, that question.
I want to get that.
We want
I
to
think you want me to
approximate.
answer that.
We want to approximate y.
Okay, boom, you want to approximate that. Right? That's what I want to do. What do you want to do? Approximate that. Okay, what information do you know that will help you? Well, I'm given this information, and I'm given this information. Okay, now start to examine each piece of information. What does this mean?
The way you word it, the test I wasn't sure. It said you got it from 3.1, from PL 3.1.
Yeah, I left that out. It doesn't even matter.
But how is 3.1 and this one related?
The fear of
It doesn't matter. I'm telling you this, but I said how I got it is through this. How I got it wouldn't be irrelevant anymore. No. You know this. So I might ask you, okay, so what do you want to do? I want to approximate that, right? That fixes a goal in your mind. Once you have a goal in mind, it gives you a direction to head in, right? You always know where you're supposed to end up. So you never get so flustered and confused in the exam that you try a bunch of things not knowing where you're going, running like a chicken head off. So you always, with his head cut off, you always set a goal. What do I want to do? Boom, establish that goal, fix your eye on that goal. So now you know where you're heading at any given time. No matter if I say 5 minutes left or, oh my God, you're freaking out, your palms are sweaty, you know where you want to go. That's going to help you stay calm because you can sort of envision the goal. The next thing I would probably ask is, what does this mean, right? So you know the information you're given, I'm going to say, so what does this mean? I'm going to give you that look, right? What does this mean?
f of x plus delta x upon 2 is equal to 0.
Too complicated.
Yep.
Think simple.
Isn't that
This is x and y.
when x is 0.1?
Exactly. When x equals 0.1, y equals 0.4. That's what that means, right? But that's something you'd have to ask yourself, right? When I give you the information, it might look confusing. What you do is you just ask yourself a question, what it means, and your brain will start to figure it out. Like, what does this mean? That's what it means, right? Okay, so I know for this x value, the corresponding y value is that, okay? That's still my goal, but I know this, right? Because I asked myself, what does that mean? What does that mean? Okay, what does this mean?
Your initial value.
Its initial value. Again, when I say what does this mean, you should explain in a sentence that seems more understandable to you in English. This is the same thing. When x is 0, y is 0. Okay? What does this mean?
The rate of change, y.
So you start by explaining what is dy dx? What does that mean?
The rate of change of y in respect
Simpler,
to x.
what is it?
Slope.
Slope. Another word for slope.
Tangent. No.
What's another word for slope?
Rate of change.
Derivative. Okay? Now, what does derivative mean? When you're back in Calc 1, derivative, there are two notations you got for it. What is?
D over dx and
You can write it as dy dx. What's another way you could write it?
Y prime.
apostrophe.
Y prime, right? Now you link this with a prime, which shows up in this formula. Oh wow, now I'm seeing that this connects to that formula here.
Okay.
You see what I'm saying?
A little bit.
So when you're totally lost, just start asking yourself questions. Where do I want to go? What do I know? What does that mean, right? What's another way I could write this? What's another way I could phrase that? Oh, now once you get another phrase, it connects to another piece of information you know. And you sort of build on that, right? That's how you dig yourself out of a hole. When you see a question, you're like, oh my God, I don't know what to do. Start asking yourself questions. What do I want to do? What does this mean? This information you're telling me, how can I rephrase it in another way, right? Now, when I ask those questions, I know it seems sort of vague, especially when you give me a look, it's going to freak you out. But it's very important. Those are the kinds of questions you ask yourself, right? Now, usually, if your answer is too complicated, you don't want to do it. You want it to be able to rephrase things in layman terms, something that if someone's talking to you in everyday language, you would get, right? So when you're asking yourself these questions, your answer should be that kind of answer. Because the problem why you don't know what to do in the first place is because it's complicated. You don't want to rephrase it in another complicated way. You get what I'm saying? You end up in the same boat. So every piece of information you're given, express it in a different way that's a lot simpler, right? And then you'll be able to see things connect that you never saw before, right? So yeah, there's a reason why I asked you a question, try to make you feel uncomfortable, right? I want you to learn to do this process, right? So think about the questions that I asked and what they mean and how does it actually help you to connect with them, right? No question I ask you is random. There's always a reason. Figure out the reason, and you'll do much better in the end. And if you feel uncomfortable,
Wait,
that's
can
good.
we go over that problem, please?
What?
Can we do that problem?
Finish it.
I actually did this, no?
No.
We'll do it another time. Don't worry. Try yourself. Try the method of figuring out what it means. Do it. Yeah, good practice.
Please do it.
So now if you learn that, if this is what I'm telling you, something that's new to you, it's something you should practice. So practice on that problem. Here you go. Move on to chapter 4. The test is up to chapter 3, by the way. Right, the list of topics and the review problems tell you where the test comes from. Qualitative methods. That's the whole thing. By the way, there are many ways to calm yourself down, which you guys should know.
Breathe in and out.
Breathing is very important. Learn to meditate, very important.
Good night's sleep.
Yeah,
What
yeah.
else you got? What else you got?
Hmm?
What else you got?
It's not working.
I feel all of that goes up.
You know.
Yeah, because you guys lose control of your mind, that's why. You guys have to understand, there are two levels of thinking that you have, right? One is reactionary. I think they call that fast twitch thinking. That's the kind of thinking that says, you know, if you hear a roar, just run, don't think about it, right? There's the other kind of thinking that you have, that's reason, where you sit down and you deliberate,
I
right?
have no reason.
Oh,
I hear that
you
one.
need to learn
I'm
to get
kidding.
reason, right? The problem with a lot of people is they use the different kinds of thinking in a situation where they're not supposed to be used. Like when you're supposed to be thinking fast, they do the deliberation. And when they're supposed to be deliberating, they react, right? So that's a problem, right? So you have to, sometimes you have to realize that one thing that your reason will tell you is that your fears of something is very usually worse than the actual thing, right? So if you think of, you know, Jhevon staring at me is intimidating. That's not just something you'll react and like freak out. Say, why am I freaked out that he's staring at me like that? What is he gonna do? Is he gonna punch me? Is he gonna bite me? No, none of that is logical or reasonable to assume that. Why would I be afraid in this situation? And then you ask yourself, yeah, there's really no reason why I should be afraid. Like, I'm not gonna get hurt at all, right? So when you start to freak out, just calm yourself. Like, really, why am I freaking out?
Because you want to pass.
Okay. Then ask yourself, what's the worst that can happen?
Fail.
Okay. And then what?
Become
You
homeless.
get no job.
And arrange marriage.
Yeah, your family kicks you out of the house, you get disowned, right? You become homeless. Like everyone, your life just goes to hell in a handbasket, right? And then like 50 years down the road, when you have your children and grandchildren, or you're on your deathbed, your one regret in life is going to be that one calculus test that you failed, right? It's that big of a deal.
Yeah.
It is.
Try being a
Right.
happy girl. I'm
Right.
telling you, it's a big deal.
Right.
When they ship you off,
Yeah.
you failed.
So when you start to think of that, like, why am I freaked out right now? What is the worst that can happen, really?
I'm not trying to.
I won't get a good job for years.
No, that's
I
not.
won't make
It's
any
not
money
gonna
in
happen.
Yeah.
One math test does not affect your life in any meaningful way. Trust me.
Yeah, what about
One math class also does not affect your life in any meaningful way. Spending an extra semester to finish a bachelor's does not affect your life in any meaningful way. Spending an entire year extra to do your bachelor's does not affect your life in any meaningful way.
Jhevon, when you're doing our final grades, please don't think like that. Like when you're sitting there.
No, I have to think how I have to think.
Oh no.
Right? Learn to calm yourself down and realize what are actually the consequences here. Right? It's not that big a deal.
I want to be as calm as Jhevon.
I need you to talk to my dad.
Yeah.
If your son fails, it's no big deal. It's nothing.
No, there's a difference between failing at literally everything and failing on one test or one class. There's a difference. Right? That's what I said.
Not according to the city now.
According to life, okay, which is the ultimate judge of anything. Okay. So yeah, first we're going to do qualitative methods here. I want to talk about the difference between qualitative and quantitative. So what do you think the difference is?
Qualitative includes quality, and quantitative includes quantity.
Don't define it in terms of, like, what are some things that are
Numbers.
quantified? It can be numbered.
They're
Can be
usually
numbered, counted.
it's discrete,
That's a fancy.
Is it always discrete? Nah.
meaning it's not,
It would include discrete
it's
things,
not
sure.
continuous. Like
Okay,
qualitative.
can be measured.
Measurable.
Right? What about qualitative?
Continuous.
Can't be any of those things. Can't be counted, measured,
Texture, property.
etc. Right? Now, the difference between these are the kinds of things you can, in math, these are the kinds of things, you say you're doing a quantitative method when you're solving numerically or algebraically. This sort of refers to like pictures, graphs, colors, right? All the nice stuff that you don't have to think very hard about. I can say, you know, I have 5 strawberries, but strawberries are so delicious.
Oh my god.
And how do I measure delicious? You can't, right? Because not everyone's going to agree. They're not that delicious, right? But there's a difference between measuring something and using some sort of quality that it has, right? And that's where we're going to go now. We learned about solving differential equations algebraically, using separation of variables. We learned about solving it numerically, using approximation methods like Euler's method and all that stuff. Now I'm going to show you how to use graphs and pictures to think about the solution. Sometimes the number itself doesn't matter, but you want to see an overall trend, right? That's where I'm trying to get at. So if that's the situation you're in, sometimes going through these processes, it's a waste of time. You just sort of want to get an overall picture of what is going on, right? And that's where qualitative methods come in. So we're going to use qualitative methods, graphs, pictures, you know, fuzzy ideas to sort of tell what's going to happen to a solution to a differential equation, right? And there are several topics in a math class where I think the best way to teach you is to actually go through an example and tell you what I'm doing, and I'm going to do that in this case. So I'm actually going to show you by example, explaining every step of the way while I'm doing what I'm doing, why I'm doing it, and that's going to teach you how to use qualitative methods. Okay, so let's do that. I had some notes here too. Should I write those down? It's not important.
It's going to be on the side.
I don't know how it's important. Just in this chapter, we will look at ODEs of the form dy dt equals g of y. Right? This means our derivative is a function of y, only there are no x's mixed together. We could do this in that case, but in 209 we don't do that case. Right? So this is only a function of y, only a function of y. No t's. Okay. This kind of ODE is called an autonomous ODE. Is it amos or numus? Numus. Okay, that do I have to tell you about? No, I don't think so. We'll explain that. Also, for this section, you need to recall. So here are the skills you need to know for this section, where if you're having trouble with this section, odds are you're having trouble with one or more of these skills. You need to remember how to graph functions. In pre-calc detail. Right, so remember how graphing of functions you did in pre-calc? You didn't really care about the concavity and all that. You just need to be able to sketch something really quickly, right? So I'm going to give you like a quadratic or a cubic. You just have to do a sketch. You're going to need to remember how to sketch these things, right? So you're going to need to remember how to graph functions, not in super detail like in Calc 1, but in pre-calc detail. You're going to need to know how to solve equations, especially quadratic and cubic equations. Hence, you're going to need to remember how to factor things. You might have to factor things in order to draw them. Factoring is one of the easiest ways to figure out how to draw something. Because that way you can figure out your x and y intercepts not easily when you factor. Also recall some ideas, like for example, if your derivative is positive, what does that mean?
It's a positive slope.
Increasing. Right, so this means f is increasing. If the derivative is negative,
The function
it's
is
decreasing.
decreasing.
Right? So derivative positive means you're going up as you move from left to right. Derivative negative means you're going down as you move from left to right. Ideas like that you need to know: increasing, decreasing. You need to remember concavity. What does something that's concave up look like, or what does that mean?
Like this, the tangent line is below.
The tangent line is below the curve. So concave up, you think up like a cup. Right? Up like a cup for water. Okay. What about concave down?
Down like a frown.
Down like a frown. That's right. Concave down means your shape is this way. Down like a frown.
You can do that yourself.
Nope, I didn't. I'm not that creative. Right, but ideas like that, very fuzzily, like I said, not huge detail. We're going to be doing calculations, but as far as previous material goes, these are the kinds of ideas you're going to want to familiarize yourself with before attacking this chapter full on.
What about asymptotes?
Asymptotes, not really, no. There are a couple of problems on asymptotes in the homework, but on a test or quiz, it's unlikely that I'll give you anything with an asymptote. So, keywords. So you're going to look for words like, I'll actually say use qualitative methods. Right? So if a test says use qualitative methods to blah, 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 you're going to want to do what I do in this chapter. Right? Or I might say use graphs. Usually it's to solve some sort of ODE. I also might mention something like the graph g of y, right? So that phrase g of y, it's actually a notation that your textbook actually uses to talk about the derivative in this chapter, right? So if I mention g of y, or use qualitative methods, or use graphs to do blah, I'm talking about chapter 4. So this is stuff you need to know, keywords you need to look out for in a word problem, because something like this I'll give you in a word problem. Okay. Moving on. So, example. So I'm going to go through this example. I'm going to tell you everything you need to know about how to attack this kind of problem. It's the same thing that you'll do for every problem of this type. Sketch the graph of the solution to dy dx equals y times 4 minus y, where y of 0 is equal to 1. So as I said, another way I could phrase the exact same question, I could say something like, use qualitative methods to graph the solution to blah. Or I can say, use qualitative methods to describe the solution of blah. Right? So all these words, I'm asking you to do the same thing. Okay. So let's actually take this in steps. Step 1. Find the steady states, which from now on I'm going to abbreviate SS, and inflection points. Okay, now what does that mean?
That means you find the derivative and then you set the derivative equal to 0.
Right, SS is the y values for which dy dx equals 0. So basically, in step 1, you're going to set this equal to 0, solve for the y values. Okay, that's one thing you're going to do. So that's what you're going to do for the steady states. For the inflection point, how do you find an inflection point?
Find the second derivative.
Find the second derivative. Now remember, the problem gave you the first derivative, right? Which means to find the second derivative, I'm going to have to differentiate that. So then find second derivative. IP are the y values for which y double prime equals 0. Okay. So step 1, find the steady states and inflection points. And this is how you find them. Okay. So for this problem, I give you this. Use qualitative methods to find a solution here. First thing you're going to do, boom, equals 0. Y times 4 minus y equals 0. This means, what is y? 4. These guys here are steady states. Right. Now what if I want to find inflection points? What do? Right, I know y is equal to, I know g is what we call this, is equal to y times 4 minus y. I can expand this, 4y minus y squared. So g prime is equal to 4 minus 2y. Set that equal to 0. What do I get? Y equals 2. This is inflection point. Okay. For quadratics, your inflection point is always going to be halfway between your two steady states, if you have two steady states. Only for quadratics. That doesn't work in general. So that's actually step 1. Okay? Find the steady states and inflections. To find steady states, set the original guy equal to 0, solve for the y. To find inflections, differentiate that with respect to y, set that equal to 0, and solve for the y. That is step 1. Step 2. Draw what we call a stability graph. i.e., a graph of y prime versus y. Right? I'm going to actually graph the picture of the derivative, not the answer. Right? So basically, I'm going to graph that graph over there. Right? Where okay, how do I graph that graph? Quickly, explain. So here, this is y prime, and the horizontal, I want it to be the y value. How do I graph that graph? Y times 4 minus y.
Well, you know y 0, you get 1.
That's not irrelevant at this point.
First, you should plot the points.
Plot what points?
So 2, so 0, 2. I think it would be a point on the graph.
No, why would that be a point on the graph?
Because that's where it turns.
Plot the points. These points I got. The first
Right,
derivative.
what would these points be in the graph world?
Right.
They would be your x-intercepts, right?
Yeah.
If you set the function equal to 0 and solve for your input values, that gives you the intercepts on the horizontal. This is why I tell you, you need to remember how to graph these. When you set the original equal to 0, get these values, those are the guys that intersect the horizontal. So there's going to be a point at 0, there's going to be a point at 4. Now, how do I draw the graph? What does it look like?
You could put a number between those numbers and see if
It's a quadratic.
Wait, how are we supposed to know what
Not worrying about that. We're in pre-calc. Remember? In pre-calc, when you know you're graphing a quadratic, what do?
well, we know the behavior of the graph.
What are the possible shapes?
Um,
It can either look like this or look like that,
Yes.
right? One of the two. Which one?
It's the second.
This one. Why is it that one?
Oh, I just plotted points.
Because
Because it's
2
negative y
is
squared.
Because it's a negative y squared. If the coefficient of the square term is negative, it's upside down.
Why?
If the coefficient of the square term is positive, it's this way.
Oh.
wait, hold
Right.
on. Where are you seeing this?
This is a quadratic. This thing that I'm graphing. This is 4y minus y squared. It's a negative quadratic. It's upside down. So these 2 points, I'm just going to draw that shape between them. That's my graph. Okay. Don't concave, look at it. No, pre-calc. Right? Think simply.
Can't
Right.
anymore.
Put in the x-intercepts, and then you draw that shape through them. Right? You don't care about, oh, pre-calc. At that point, you don't care. The inflection point is going to be where it changes, right? That's going to be a 2.
So probably 1.
Okay? So now, we'll use this at the end. You'll see where I use that. Just make sure you copy it down. Now, after you graph that graph, that's not a complete stability graph. That's just a graph of the derivative. The stability graph is what you put on it. Now, it's going to take a while for me to describe this, but in practice, it'll be really quick. You'll be able to catch on really quick. Let me redraw it here, bigger so you can see. So this is a steady state. This is an inflection point. This is a steady state. This is y prime. This is y. Your book will call this G. Okay. Now, put in stability arrows.
That's step 3.
No, we're still in step 2. This graph is step 2. I just copied that here. You wouldn't do it twice. I want to draw it bigger. For each steady state. Okay. In this way. So here's how you draw the stability arrows. 1. If graph is above the horizontal, draw a right arrow. right? If your graph is above the horizontal, you draw an arrow to your right.
Okay.
Always, right? Don't get confused, which way to look. No, just look, is it on top or is it underneath? If it's on top, you draw an arrow to the right. It will always be to the right. Every time the graph is above, draw it to the right. Graph is on top, go to the right, okay? Which way do I draw the arrows if the graph is above the horizontal?
To the right.
To the right.
Good job.
Always to the right. Yes, good job. Okay. If graph is below, left of the horizontal. Yeah, that image of me doing that is going to be stuck. Draw a left arrow.
So it's going clockwise now.
Always to the left, right? So if your graph is below, draw it to the left. Okay? So, and you're doing this for each steady state. Okay, so let me demonstrate. I draw this picture. Here are my steady states. For each steady state, I'm going to try to do this, right? To the left and right, immediate left and right of the steady state is where I'm looking, right? So look to the left of this steady state. Where is the graph?
Down.
Down. It's below the horizontal. So what do I do?
Left arrow.
Draw an arrow going to the left. Move over here. Where's the graph?
Above.
It's above the horizontal. So what do I do?
Right.
Draw an arrow to the right. I've just drawn stability arrows for this steady state. Move on to the next one. I'm to the left. Where do I draw the arrow? To the right. Why? The graph is on top of the horizontal. Move over here. Where do I draw the graph?
To the left.
To the left, because the graph is below the horizontal. I've drawn all the stability arrows for this graph. So what does these arrows mean?
The behavior of the graph.
It's the behavior of the solution is what we're doing. What does this mean? These arrows tell you the behavior of the solution. Right? Basically what this is saying is the solution graph, if you're above 4, the graph is going to head towards 4. If you're between 0 and 4, the graph is going to head towards 4. If you're less than 0, your graph is going to head that way. It's going to get negative, right? So these arrows at any given time is telling you what your solution is doing at any given time, right? There are some scenarios. If two arrows point head to head, we say the steady state is a stable steady state, right? And we denote that with a smiley face. I'm not kidding. So here, I'm going to draw a smiley face, right? This is stable steady state because it means our solution will stabilize at that number, right? Whether I'm above or below 4, I'm going to head towards 4. My graph will stabilize at that number. It's kind of like the asymptote I'm approaching is the number 4, right? So that's called a stable steady state. It will approach that number from either direction. This means it's an unstable steady state. That is denoted by a frowny face. Right? So in fact, over here, I'm going to draw a frowny face. Okay? This says it's never going to stabilize there. Whether I'm a little bit bigger than 0, I'm going to run away from 0 towards the 4. If I'm less than 0, I'll run away from 0 also. Right? I'm always getting away from 0. I cannot be stable there. Right? So it's called an unstable steady state. There are two other situations. If your arrows point both in the same direction, that's called a semi-stable. And that one's just like meh. Right? This means from one direction I approach that point, but if I'm on the other side, I'd run away from it. So it's half stable. Right, so step one is to find your inflection points and your steady states. The steady states give you the horizontal intercepts. The inflection points will give you the maximum or minimums of this graph. For each steady state, I'm going to write stability arrows according to this rule. If I'm above the horizontal, I always draw an arrow to the right. If I'm below the horizontal, I will draw an arrow to the left. And this is what it means. Okay.
Hope we get to draw smiley faces on the phone.
Yeah. Draw the smiley faces. Okay. Now, all of that was step two, right? It'll be quick once you get to practice a lot. It took a while because I had to write this all down. Okay. Step three. This is a 4-step process, by the way. But good news, step 3 is completely optional.
Nice.
I will not require that you do step 3.
Is it recommended?
It is not even recommended, no. Step 3 is sort of a part of it that takes out some intuition, but I think the intuition is sort of easy to pick up on anyway. So step 3 is for people who just don't want to think about it and just do some calculations to tell them what to do. But I'm going to show you an intuitive way to figure out what you can figure out from step 3. Okay. So step 3 is where we're going to analyze concavity. I'm going to show you anyway because some people actually prefer doing this. Right? You analyze it by looking at the sign. Of G prime times G. Okay. Now remember, G is basically your graph, right? G prime is the slope of the graph, that graph that I just drew. Can I get rid of this? Can I also get rid of this?
Yeah.
I want this graph to stay here so you can see what I'm going to do. So here's what the analysis means. If G prime times G is positive, that means concave up. If G prime times G is negative, that means concave down. So I'm actually going to do that, and I'm going to keep track of it in a table. So you're going to put on this table, and what you're going to do is you're going to put your steady states and inflection points on this table. So here my steady state was 0 is a steady state, 2 is an inflection point, 4 is another steady state. Now you think of these as intervals, right? So this is describing minus infinity to 0, this is describing 0 to 2, this is describing 2 to 4, this is describing 4 to infinity, right? I'm trying to see what is the graph doing on each interval. So what I'm going to do is I'm going to pick a random number in each of these intervals, and I'm going to examine that number, right? So let's say over here I pick, say, -1 to test, right? What I'm going to do is I'm going to find g of -1 times g prime of -1. Okay. I don't have to actually even compute it. I can tell all that information from the picture, right? So if I'm here at -1, where's my graph? It's a negative, right? It gives me a negative value. So G is actually a negative. What is the slope of the graph doing at this point? Is this a positive or a negative slope? That's a positive slope. So my G prime is actually positive. Negative times positive, negative, which means concave down, down like a frown. Right? Okay. Do the same thing over here. I can test, say, 1. If I come over here, my 1 would be here. So at this point, what's the graph? The graph is positive. Now I look at the slope at that point. What's the slope of the tangent line? Positive or negative? So again, positive. Positive times positive is positive, so this means concave up, up like a cup. Pick a number in here, like a 3. I'm going to look at g of 3 times g prime of 3. So here it's 3. What's the graph? Positive. Draw a tangent line. What's the slope? Negative. Positive times negative is negative. Concave down, down like a frown. Pick a number over here, like a 5. I'm going to look at g of 5 times g prime of 5. So my 5 would be over here. The graph is negative. Draw a tangent line. The slope is also negative. Negative times negative is a positive. This means concave up like a cup. Now I'm going to show you how you can figure out concavity without doing this. But if you don't want to think about it, this is what you do. And that finally brings me to step 4, which is draw the solution graph. Okay. This means, i.e., graph of y versus x, or did I use t here? I don't remember. I used t. We'll very usually think of it as time being the variable, and y is describing a population or something like that. So it doesn't matter what I use. So because we'll often use populations, I only care about the right side of the graph. So I'm going to think of the graph as here. This is my y-axis, and my t is here. Now what I'm going to do is I'm going to put in all the points I found. What are my steady states, inflections, and all my steady states? So 0. So at 0, draw a broken line that goes right across. Y equals 0 is a steady state, right? I have another steady state at 4, right? At 4, draw a broken line. That's another steady state. At 2, draw a broken line. This is an inflection point. Okay? Now we're going to put everything together, and what we're going to do is at this point is where the initial condition comes into play. So I'm going to start off my y value at a certain point, which is what I told you in the beginning. When t was 0, what was the y? I said y of 0 is equal to 1, right? Yeah. That means here's my starting point. This is y of 0 equals 1, means that's the starting point of my solution, my function. And now I'm going to draw a picture of what this guy would look like. And what I'm going to do is I'm going to use both of these. Okay. So now, if I'm at the point 1, what should I be doing?
Going up.
Going up. Why am I going up?
Because the slope.
Because 1 means I'm right here, and this arrow tells me go that way. Right? If I'm at 1, I should be heading towards 4.
Yeah.
So I'm going to be going up. Now the question is, how am I shaped while I'm going up, right? Here I'm in the interval 0, 2. So what should my concavity be?
Up.
I should be up like a cup. So I'm going up, but I'm shaped like a smiley face while going up. Ooh. Okay? Of course you stop at an inflection point, because what happens at an inflection point, right? So I increase concave up until I get to that inflection point. Now I'm entering a different interval. The interval is 0, 2 to 4. Now when I'm in 2 to 4, what's my concavity? Now it's down. Where should I be going?
Towards 4.
Between 0 and 4, the arrow still says go that way, keep going, right? So I'm going to continue to go towards 4, but now I'm increasing concave down. So I'm going to switch to a frown as I increase. And I'm going to stabilize at 4.
And then I'm assuming it also stabilizes at 0.
Well, we'll talk about that. So this is the initial condition, and this is what the graph of the solution is doing. So if I were to solve that differential equation and then graph the solution, that's what a graph would look like, right? Which is crazy. We did it without even solving the differential equation. So I'm always going up to 4. Now, the question, I can actually ask you any initial condition I want. I could say y of 0 equals minus 1, in which case I start here.
But you would still go up.
Well, look at this graph. If I'm at minus 1, where should I be going?
No.
Yeah.
I'm going that way, going away from 0. It turns out my graph is going to do this. It's going to go away from 0. What if I said y of 0 is 3? Means I'm starting here.
Going to the right.
So when I'm at 3, I should be going towards 4. So I'm still going up. And I already know my concavity is like a frowny face. So that's what the solution would look like there. What if I said y of 0 equals 5? Which means I start here. If I'm at 5, the arrow says go that way, go towards 4. So I should be decreasing towards 4. So that would be the answer. Right? The arrow's telling me where to go. Now, I could use this table to tell me about concavity, but as I'm going to explain to you now, it's pretty much intuitive. Here's the idea. These steady states, you want to think of them as asymptotes.
Okay.
So you want to approach them but not touch them. Right? Now, if I'm increasing and I'm looking like a smiley face while approaching 4, what's going to happen? Right? If I'm on a line, right, and I'm increasing this way, what's going to happen?
Going to reach
I'm going to just crash into it, right? I can't level off if I'm shaped like this. I have to shape like this in order to level off because it's an asymptote. Therefore, I can't just go like, I'm going to crash into the fence. I have to be swerving this way to not crash. So when I'm in this region, I have to shape like a frowny face. There is no choice because a smiley face would crash me into it, right? So I know without even doing that table, I need to be concave down in this region. This is an inflection point though. So if I'm concave down here, what do I need over here? I need to be concave up, right? So because I know I need to level off here with a frowny face, I know over here I need to be a smiley face so that I switch here to a frowny face. I didn't need the table to tell me that. Same thing from up here. I can't be decreasing concave down because I'm going to crash. I need to decrease this way so I can level off, right? So I know over here the concavity has to be concave up, right? Here, you want to run away from 0 just as fast as possible, right? If you're decreasing like this, it's a slow deceleration, but this graph always behaves quite violently. Same thing here, you'd have to be concave down to level off, and that's sort of your issue. So really 3 is sort of optional. You could actually draw this and figure out how your graph needs to look. So next time, we'll run through an example of this quickly where I don't have to explain everything. It really gets quick once you get the method down. Test on Monday, do the review problems, watch those videos.
There's no homework?
No homework. So, all right. So see you guys on Monday.
So what exactly is this? Then what's the percentage?